Okay, so yesterday we were looking at general second order systems with general damped poles, and we looked at the effect of the pole locations on the response of the system. So here's what we did. I told you that if you have a general second order system with two complex poles, then you can express the location of these poles by using either its Cartesian coordinates, which are these A and B numbers, or you can use the polar coordinates. In that case, you talk about the damping ratio and this theta angle. And instead of the theta angle directly, we use cosine of it, and the cosine of that theta has a special name. We call it damping ratio. So if you use this A and B coordinates, then the general response of a second order system with poles located at minus A plus minus BJ is will look something like that. Okay, so the C and D here are some constant numbers, and they depend on whatever you have on the numerator. But this part does not change. So you have some exponential with A here, and then you have some oscillating terms with frequency B. Okay, so these are the common characteristics. And again, here we see that the stability of the response is determined by the A number. So the B has no effect on stability because it just gives oscillating terms. But depending on the sign of the A, you may have either growing oscillations or shrinking oscillations. And if A corresponds to a pole on the left-hand side, then we have shrinking oscillations, which corresponds to a stable system. And the pole, if A is on the right-hand side, then our oscillations grow with exponential amplitude, in which case we have an unstable system. So yesterday I showed you some responses I generated using MATLAB. Today I would like to show you some more of those responses, because I think this is what makes it easier to understand. Okay, so I have coded each possible case here. First, let's take a look at this case where I vary A. So the B is constant. So it's this case exactly. Since the B is constant, the oscillations frequency will not change. So for all possible A values here, what changes here is the oscillations, the envelope for the oscillations. So let me just run this case, and so this is a free response, which means we are releasing the system from an initial condition. Well, you can here see that the frequency of the oscillations does not change. It's just that every single pole has its own envelope. That's what's different here. Okay, so and I use this color coding so that it's easier to follow. Okay, so let me just put it here. So here you see that we are varying the real part of the poles. The complex part remains the same. The second case is the same system, but now we have the step response instead of the free response. So the system starts from zero initial conditions, and it's given a step input. And as you see, the result is the same. If you compare the two figures, here it starts from some initial condition and the system converges to zero. In the other case, it starts from zero and it converts to some constant number. But the general characteristics are the same. So the oscillations have the same frequency. We have the peaks occurring at the same time instant, and we have these crossings occurring at the same time instant. But the amplitude of the oscillations change at different rates. Okay, so the next case was changing the B location. So here what we're going to do is we're going to choose a fixed A number and then change the B quantity. And changing the B quantity will make sure that since A is constant, the oscillations will be occurring within the same envelope. If the envelope is something like that, it will be oscillating at different frequencies. So let me run that case. So you can clearly see that there is a fixed envelope, but the oscillations are always within the same envelope. So this is the other response. Let me see. This is also step response. It starts from 0 and converges to some constant number. So let's run the free response for that case. The same thing is happening. The oscillations are within the same envelope and start from initial condition and converges to 0. And then, so these are what we observe by using the Cartesian coordinates. So let's see what happens if we vary the polar coordinates. Okay, so in this case, I'm changing the damping ratio, and I keep the natural frequency constant. So what that means is, if I have a certain natural frequency omega n, the omega n does not change, and I only change this damping ratio, which is cosine of that angle. So that means the length will remain constant, so the poles will be moving around a circle like that. Okay, and let me just use the other one as well. And in the last case, I'm going to change the natural frequency, and I will keep the damping ratio constant. So the damping ratio, if it's something like that, a fixed angle, then the poles will be moving along a straight line like that. And let's take a look at step response. Let me also run the pre-response for that. Okay, so the good thing about yesterday I tried to explain this. If you use the Cartesian coordinates, everything is related to time. So if you want to change something with respect to time, then it is easier to do that by using the polar coordinates. What I mean by that is the following. Let's say we're happy with this envelope, okay, and we're happy with the fact that the response is going to be oscillating within the same envelope. We just want to change how fast the oscillations occur. So instead of having the first peak occurring at this point, if you want to have it at a later time instant, then the thing to do is to change the B number. Or if you want to change the envelope, then changing the A number is what we need to do. But the damping ratio has the following power. So let me show it one more time on. So here the damping ratio is constant and the natural frequency is changing, right? So what damping ratio constant means is the following. Here, all these responses have the following characteristic. Each peak has the same ratio with respect to the previous peak. So if you have a cycle, an oscillation within, let's say, 3 degrees, and if the next cycle is 2 degrees, so that ratio does not change as long as the damping ratio is constant. So for the red one, which corresponds to that pole there, So the second peak occurs at this level, minus 0.16, and all the other peaks happen at the same level. In fact, it becomes obvious when I zoom in like that. So you see that all the peaks return from the same point, but they the peaks happen at different time instants. So I think we should probably take a look at cases similar to this. Suppose that we have a system, okay, so this is our baseline system. The poles are here, and we have this response. And we want to change this response. And I would like each one of you to be able to analyze the cases like that. For example, if I ask you to estimate the response of a system when the poles are shifted that way. In fact, if you look at past exam questions, you will see questions similar to that. You should be able to tell that without making any, Laplace transformations and inverse transformations, any of that. So to be able to do that, all you need to do is to just keep this equation in mind. This one, okay? And you don't even need to memorize that. If you have a Laplace table, you will immediately see it from the table. So let's take a look at this case. I'm shifting the A number, right? The real component of the poles are changing, which means the A number is changing here, and that A number will change the envelope. Okay, so let's try to guess the response here. Okay, so first consider the blue one. The blue one seems to have an envelope like that. If I change the poles to the red ones, the envelope will be like that. It will be converging faster. Alright? And since the vertical component is the same, the frequency will not change. That means the peak will happen at the same level here, at the same time instance, in other words. So that means the response will look like this. And since the frequency is the same, so the peak will not shift, or the peak here, it's hard to see here, but there's another peak here. That peak will also happen at the same time instant. And let me run that, and this is the actual response. Okay, so I think it's important to know these relations, because once you know that, it will be a lot easier to work with control systems. Because what we do in control systems is we play with these pole locations. And this goes both ways, by the way. So if you have the pole locations, by using them, you can predict the response. You can go from here. You can go from here to those plots. And if you know the relation, you can go backwards, which is what you will do in the lab, by the way. So in the lab, you will be giving inputs to the system, and you will record the responses. So in that case, you will have these plots obtained from the experiment, and from these plots, you will go back to these pole locations. Okay, so once you know the relation between the two sides here, you'll be able to go back and forth. And that will allow you to predict the dynamics of the system by just looking at the response. And obviously, once you understand that relation, the next level will be to modify that level. Okay, so by designing controllers, if you take the elective courses on control systems, you will learn how to shift these pole locations by means of designing controllers. So that way you will know where to shift them. Okay, so if so in fact this is a good example. If your response was the blue one, and you thought that there was too much of an overshoot here, and you don't want that, but you're happy otherwise with the speed of response, then the changing the poles like this will solve your problem. A good example here is the elevator controller. So if you have an elevator, the elevator will reach a floor and you want it to stay there. So if you have a response like that, it will overshoot and then come back again to the floor you want to reach. So since that's not a very comfortable controller, obviously you don't want such an overshoot, so you will prefer to have a response like that. Okay? Hızları well, the oscillation rates are constant, right? Otherwise, they have different envelopes. So let's take a look at this one. What do we do? So here I'm changing the A number within a larger interval. It starts from 0 and goes all the way to this. You see that settling timeları farklı. Well, what changes here is we're changing that A in the equation, right? So the oscillations die out a lot faster if you move the poles farther to the left. It reaches this state faster. Okay, so let's take a look at this one. Now I'm going to shift the B or the imaginary component of the poles. So I'm going to move poles like that. So that will change the frequency of the oscillations, and the envelope will stay constant. So let me just try to plot an envelope here. If the envelope is something like that. So the envelope will not change, but for the red one, it will be oscillate at a faster frequency. So if the first peak occurs here, in the other ones, the first peak occurs somewhere here. But since it has to be within the same envelope, the response will reach a higher peak like that. And it will be something like this. Let's take a look at the actual response. Okay, so this is just like we predicted, right? So by increasing the frequency, we made the response faster since the oscillations are now occurring at a faster rate. But this was not a very good response, right? Because now we have the system reaching a higher peak. So even though it is faster, so it reaches this level much quicker than the blue one, but the problem is it hits a higher peak, and this is obviously not a preferred response with respect to the blue one. So if we are happy with this the blue peak here, and if you want to make the response faster without overshooting more, then what we need to do is we need to keep this ratio constant. Okay, so the first peak reaches 1.2 approximately. So we're happy with that number. Okay, so we want to keep that level, but still want to make the system faster. So what we need to do in that case is we need to keep the damping ratio constant, because we want this the first peak level occurring at the same level, and increase the natural frequency. Okay, so the same one, and I'm going to change natural frequency. I'm going to keep the damping ratio constant, so that means this angle will not change. But I'm going to increase the natural frequency. I'm going to put the poles somewhere there. And what I expect to see there is I expect the peak to stay where it is. And I want to be able to reach there faster. So I expect the response like that. In fact, this is exactly what we get. If you zoom in here, you see that the peaks are more or less constant. Okay. So if you look at these last three cases, you see that it is easier to shape or reach our target response by changing the damping ratio and natural frequency rather than changing A and B. Because when we change A and B, something changes, but the other parts of the system doesn't change in the way we expect it to change. Yani bu son şey ona güzel bir örnekti. Şurada. Mesela biz hızlı olsun diyoruz ama hızlanırken aynı zamanda daha yüksek bir yerden dönüyor. Çünkü envelope'unu değiştirmedik. Yani envelope sabit kaldığı için. O yüzden onu yani damping ratio ve şey daha doğal, daha makul şeyler sunuyor. Çünkü öbür tarafta dediğim gibi iki şeyi farklı değiştiriyorsun. Oysa ki gerçek hayatta biz ikisi aynı anda makul yani benzer özellikleri koruyarak değiştiğini istersek natural frequency ve şeyi değiştirmek daha makul oluyor. Okay, so I can tell you for sure that in the final you will have to demonstrate this somehow. So I already asked these questions before. I asked shifting the real component of the poles or the imaginary component of the poles, and in this exam it's quite likely that I will ask something like that. I will ask you to change the damping ratio, and you should remember this response. Okay, so the peak should not level of the peak shouldn't change, only the time when you reach the peak should change. Okay, so this completes the discussion on second order systems. So we discussed first order systems and second order systems. And the good thing about linear systems is it is sufficient to know this much. Because if you have higher order systems, then it will be composed of a number of real and complex poles. And due to the superposition principle, you will be able to solve the system by knowing only the response of first and second order systems. So if these are the poles, then you know how the response will look like. And if you have a third pole, a real pole here, or two more poles, you can divide the system into different by partial fraction expansion, and you can analyze the individual responses and then sum all of those individual responses together to get the overall response. Bir şey diyecektin Arman. So at this point you may have a question like this in your mind. We spent quite a lot of time on discussing these first and second order systems, but in reality most systems are higher order, especially if you consider complex modern systems. They have many components, and that gives you a higher order system. So what I said last is helpful here. So you can, if you assume your system is linear, which you can always do if you can keep the domain of your operation small enough, your system will behave like a linear system. In that case, you can divide the system into first and second order systems and then take a look at the responses. That will give you an idea. But what happens in practice is the following. You may have a lot of poles in your system, but they will not be concentrated in a small area. So what will happen in reality is the following. You will have, for example, these poles, so they are at, let's say, -1, and then you have this real pole at -10, and you have this some additional poles, but they are much farther away from that. So if this is at -1, and if you have some poles at -100, so let's think about a system like that. You will have individual responses, and this response has a time constant of 1 second. Okay, so the response will reach steady state within 3 or 4 seconds. But response due to these poles, they have a time constant of 10 milliseconds, right? 1/100 is 10 milliseconds. And the response due to these poles will be reaching a steady state a lot quicker. So they will reach a steady state within 0.1 seconds, something like that, on that order. So in systems like that, if you plot the response of this system, and if you plot the response of this system where you remove these poles to the left, the response will be very, very similar. Because since these poles will be reaching steady state very, very quickly, the transient will be determined by the slowest poles, in other words. So in most cases, it is sufficient to consider what happens to the slow poles, because the fast poles will be, and they're stable since they're on the left-hand side, they will just quickly settle down, and the transient will be shaped by the slowest poles. And we call these dominant poles. So what I'm saying here is, even if you have like a 10th order system, if you look at the response, it will look very much like a 2nd order system, because out of those 10 poles, the 8 poles will be fast enough and they will die out. The responses due to those poles will die out very quickly.
Orada genel bir şey var mı? Şu kadar yarıçaplık bir yarım dairenin içindekileri alıp diğerlerini alamıyor diye, yoksa bunu gözlemlememiz lazım?
Ya onu kendin çıkartabilirsin mesela. Şu time constant şeysi o açıdan çok faydalı. Mesela bunun time constant'ı 1 saniye, 3-4 saniye boyunca bir şeye bakarsan onun etkisini göreceksin. İşte yani mesela şununki onun 10 katı daha hızlı. 0-1 saniye, 0-0-4 saniye. Yani o ilk baş şeyde yok oluyor. Tabii kesin bir limit yok yani. Yani şuraya bir çizgi çizip bunun sol tarafındakileri hiç düşünme, ama onun hemen sağını geçtiğin zaman hesaba katman lazım diye bir şey yok. Orada yani yumuşak bir şey var, sınır var. Mesela kimi durumlarda çok hızlı yani ilk baştaki response'a çok önem veriyorsa, ona çok dikkat edilmek istiyorsan, o zaman tabii hızlı şeyleri de bilmende fayda var. Yani so let's say your response looks like that. The response due to these poles, so let me use different colors here and make these red. The response due to the entire system, including the red poles, will have only variations within the very first like half second or so, and the rest of the response will follow the response of the original one, because these are so the variations after this time will be only due to the slow poles. So if you want to analyze very accurately what happens in the first initial response of the system, then you should be including these fast poles as well. Yani hep diyorum, deneyde onu da göreceksiniz, bunu da göreceksiniz diye. Bunu da aslında göreceksiniz şu açıdan. O deney çünkü aslında ikinci derece bir sistem değil. Deneyin manual'ına bakarsanız orada var ki benim daha önce derste de onun denklemlerini yazmıştım. So theoretically that's a third order system. You have one pole due to the electrical part of the system, and then 2 poles due to the mechanical part, the ball moving up and down. But it turns out that the electrical part of the system is very, very fast. So when you apply a voltage, the current reaches steady state under the order of milliseconds, whereas for the ball it is slower. Yani oradaki şey çok güzel bir örnek. Orada üçüncü kök hiç yokmuş gibi düşünüp sadece 2 köklü bir sistem üzerinde yapacaksınız. İkinci derece sistemmiş gibi. bakacaksınız. In fact, the system there is even higher order. It's not even third order. It's at least fourth order and could be even more. Heyecanla bekliyor musunuz deneyler? Ben çocukken öyle bir deneyim olsaydı var ya hiç gece gündüz onunla oynardım. Bir sürü değişik şeylere bakıp. Okay, so we have one last topic left, which is also a very important topic, and that will certainly be included in the final exam. So let's make a very quick introduction to that topic. Neyse onu boş vereyim de. Okay, so suppose that you don't have any computer or any calculator, just like in the exam, right? And I give you a transfer function. I give you this. I just made it up, and let's say the numerator is just 1. And if I ask you to predict the stability of the system, you can do that very easily, right? You can find the poles very easily. You know how to solve the poles of a second order polynomial. And even so anyway, you can look at the poles and you can tell me very quickly if the system is stable or not. If the poles are on the left hand side, you will immediately say that it's stable. And you can even tell more than that, right? By looking at, after you locate the pole, you can tell me how, if it's going to be oscillatory or not, or if it's oscillatory, how fast the oscillations will die out. You will be able to say things like that as well. But if I give you something like this, like an 8th order system, so if I give you a huge transfer function like that, it is impossible to do anything here without a computer, right? Because you need to locate the poles. So obviously there will be 8 poles for the system, and once you can locate the poles, you will be able to say a lot of things, like if you can place poles here. But that is not easy. So there is no simple formula for calculating the poles of a higher order polynomial. For those cases, I know when that happened, but it should be at least 100 years ago. They came up with a simple test to check the stability of such high order systems. It's called the Roth-Hurwitz stability test. So by just looking at the coefficients of a polynomial like this, you can in fact say whether there are any unstable poles or not. So this is a useful test if you don't have a computer. So nowadays with a computer, obviously you don't need to consider this test, but it still is very useful for exams, because in the exams you don't have computers. And so the last topic is this Roth-Hurwitz stability test. But the bad thing about this test is it only tells you the number of poles on the right hand side. So if you apply the test to this transfer function, in the end, the best thing you can say is there are 2 poles on the right hand side and nothing else. You can't say anything about where they are. So that means the 6 poles will be on the left hand side, but they can be anywhere. The only thing that this test gives is whether they are on the left hand side or the right hand side. Doğru. O test Doğru, yani orada yani manuel bir şekilde kontrol edilebilir. Hani öyle. Ama şu şeyden konuda çok kullanılıyor. Yine geçmiş sınav soruna baktığınızda onu da göreceksiniz nasıl uygulandığını. Mesela şöyle bir sistem veriyorum ben. İşte böyle bir blok diagram şeklinde oluyor genelde. İşte şöyle bloklar var. Bunlar böyle birbirlerine bağlı. And in these block diagrams, I give some numerical values, and then I'll give some parameters without an actual numerical value. So, for example, there's a k number here, or there may be an a number here. And I ask you, what should the conditions on k and a such that the overall system is stable? And you can answer that question very easily by using the Rath-Hurwitz test. Because in that case, you will have these k and a parameters appearing somewhere in these coefficients, and you use the test by using those parameters, and at the end of the test will tell you if these quantities are positive, for example, your system is stable, and those quantities will involve these parameters. For example, if you have something like that, k plus 7 should be positive, and then you can say that k should be greater than minus 7. So that gives you a condition on stability, condition on k for stability. Okay, so let's see. This is all about that test. Let's scroll down. So it looks like we will not have time to talk about these transient performance characteristics, like the overshoot, the settling time, rise time, things like that. But you'll have to learn these for the lab report. So I'm counting on the lab report that you will study these things on your own. And so there's also this example. If you don't have time, you already have this in the lecture notes. You can look at this example. So these are the parameters, right? There's some kPa and kd numbers here. Geçen sefer bütün bu kadar şeyi oturup tek tek tahtaya yazdığımı düşünürsek bayağı iyi konu işlemişim ya. Dedem onların hiçbirini yapmadan bir şekilde bunlara vakit kalmadı. Nasıl oldu anlamadım o iş. Okay, so this is all I would like to say for today. So you already know two questions for the final exam. One question will be something like this, and the second question will involve the Rath-Hurwitz stability test. We haven't seen that yet, but you will have a question related to that. And then there will be two more questions, and I don't know what they will be. Okay?